running that. I'll be here. So if you have questions and to get ready for the exam, it's a good night tonight. So we're going over that material. See where that will be the review session for the exam. Anybody have any questions with the format for the exam and the setup? Well, that should run just fine on Thursday. I'm hoping if everything goes well, I should have results for and your grades for the exam up and posted for you by the end of the day on Friday. I'll send out an email when that's ready to go and your grades are available for you. And also, either today or tomorrow, I'm going to go through and post your current, or up to now, your current OWL and clicker grades. So those will appear on OWL. All the grades will be run through the OWL gradebook, your first grades. So look for it there. If nothing's going to be posted in the grades on Moodle. All the grades will be located on OWL. And again, I'll send out an email when I get the OWL and the clicker grades posted. And that'll be current without any drops. All right, so that I'm not going to drop 10% and do anything like that. It'll just be current, up-to-date grade. Yeah. 20 questions. All the exams, 20 questions. Anything else? All right. So I left off on Friday going through a more complicated ice table problem, equilibrium problem, that involved the quadratic equation. Everybody's favorite. So if you haven't already, you want to see the work through the solution to that problem, see the lecture that I posted on Friday. It's all there. There's also a couple extra example problems that I run through that are also posted in that lecture that I did not cover in class. So if you're looking for extra explanations, take a look at the lecture there. This is my step-by-step breakdown. I'm going to go through another problem. This is going to be another quadratic problem. To give you guys another example of how to work through this. And again, another twist to the type of questions that I can ask as well will be included in this, and then we'll move on from there. Anybody have any content questions? All right, I got office hours today. If you have questions today, tomorrow, and Wednesday from 1:30 to 2:30, and then office hours on Thursday from 9 to 10 in the morning. Keep that in mind if you do come up with questions and you like to talk to me about it. All right, so for this problem, we have COBr2 is going to degrade to form CO and Br2. Everything's in the gas phase. And the K for this is 0.190. The problem's also going to give you my initial concentration for COBr2. That's going to be 0.25 moles per liter. And the problem simply states calculate the equilibrium concentration for all three species. And then the new question for it is what percent of our reactant has decomposed in the reaction? So how much of our starting material has decomposed or has disappeared? And so we'll need to figure that out. So just simply from the reaction, I'll put my K expression up here. At this point, this should be pretty straightforward. So we'll start filling in the ice table. We have our reactant, COBr2, and our products. This one's pretty straightforward. All my coefficients are 1. I don't have to worry about that. And I just have an initial concentration for my reactant of 0.25 moles per liter. And 0 for everything else. Because all the coefficients are 1, it's pretty simple. I'm going to lose some amount of reactant, and I'm going to gain the same amount for each of my products. And so at equilibrium, the concentration is 0.25 minus X, and X. All right. I'll just plug these equilibrium values into my K expression. My two reactants, or two products, I know what my K is. So I'll just write my x squared, and then I'll bring my denominator over. And then I'll just combine terms on the right side of the equation. I end up with 0.0479 minus the 0.190x. And just get everything over onto one side of the equation. 0 equals x squared plus 90x minus 0.0479. Going through the quadratic again, that's x squared equals minus b plus or minus square root b squared minus 4ac all over 2a. I'll substitute into that. Minus 0.190 plus or minus my b term squared minus 4. My a term is 1, and my c term is negative 0.0479. All over 2 times 1. Alright, anybody have any questions with filling this out, getting to this point? Alright. So we'll simplify all this down to negative 0.190, and then under the square root term, I end up with 0.2261 all over 2. So I have two different options because I have that plus minus value here. So option 1, I end up with, I'll have a plus, and the result of the square root is 0.475 all over 2. And it's going to give me a value of 0.1425. And option 2 is going to be the same thing, just a minus 0.475 all over 2. Negative 0.3325. So at this point, because one of the values is negative, don't necessarily throw that out. All right, just because the x is negative doesn't mean that's the illogical answer. Just keep in mind, one of these answers is going to make sense, and one of them is going to be completely illogical. But we need to substitute that back into our equilibrium expression for one of our constituents to be able to determine which one makes sense and which one doesn't. So we'll do that first. So for my products, the concentration of CO is the same as my Br2. And that equals x. In this case, it's pretty straightforward, so my options are either 0.1425 or the negative 0.3325. And in this case, the negative value obviously doesn't make sense. You cannot have a negative concentration. So this is not possible. So therefore, this is our answer for our two products, the 0.1425. And for our starting material, that was simply 0.25 minus x, and that's end up being 0.1075. So that's our concentration. So that answers the first part of the question, what are the equilibrium concentrations for a reactant and two products? Now, the percent decomposition is straightforward. It's just my equilibrium concentration divided by my starting concentration times 100%. has decomposed. So I've lost 57%. Yes. You're using your equilibrium concentration. What would happen in that case when you looked at your starting material? You would end up with an equilibrium concentration that was greater than your initial concentration, and that's impossible. The reactant concentration must decrease. That's a good question. Everyone hear the answer to the question to that? What happens if my two options are both positive values? In that case, I would substitute into one of my reactant equilibrium expressions. In this case, the 0.25 minus x. And what that would potentially give me would be a concentration that's greater at equilibrium than what I started with. And that's obviously impossible. So the concentration of my reactant must decrease. So substitute the two options in one way or another will not make any sense. It will be completely illogical. You can just throw that one away. Anybody have any questions with this type of calculation? Like I said, this is pretty much as complicated as it gets in terms of equilibrium calculations at this point. So if you're good with this, you're probably in good shape. Yeah.
With that bottom calculation, isn't that 43%? Doesn't know what that is?
Does it work out to 43?
Yeah. So when you do x, does it actually do that?
Yeah, if you put the x value, you get this. All right. Just because we haven't done one of these in a couple days, I'll give you guys a clicker to work on. Working on the same type of equilibrium concentration. This is not a quadratic problem. Don't worry about that. minute or so to get the answers in, please. If you could, keep the chatter down so people that are still working have an opportunity to get through this. All right, anybody else? Going once? Twice? All right, we'll leave it right there. So working through this, we'll go through this. This ends up being one of the relatively simple problems once you actually get into it. Our K for this expression, NO2 squared over N2O4. So I'll set my ice table. So my initial concentration for the N2O4, I can't use just the 0.1 because that's 0.01 moles in 2 liters. So my concentration of N2O4 is 0.010 divided by 2. So my concentration is actually the 0.005 moles per liter. And for my product is 0. So I'm given my equilibrium concentration for the N2O4. So that's 0.042. So I can determine what my change is. I don't need to get into an x variable. So the difference is simply 0.0008 is how much I've lost. What I've gained in my product is going to be twice that. This is why I bring calculator. 4 0. Yeah, that's right. There's a fourth 0 with. And that's going to end up being my equilibrium concentration for the NO2. I substitute that into my expression. And I end up with a value of 6.1 times 10 to the minus 4. So B was my correct answer on that. All right. And most of you, 88% of the class got that. So that looks good. All right. So this is again one of the more basic equilibrium ice table problems. So for the vast majority that got to that answer, you're in really good shape for this material. All right. The last part of I want to go back to 15.2 and just catch this, the conversion between Kc and Kp. So when you're dealing with compounds in the gas phase, so this has got to be in order to work with Kp, everything in the reaction that would take part in the equilibrium expression must be in the gas phase. So it's completely fine to have solids here because they're not going to take part in the equilibrium expression, but everything else that will be in the equilibrium expression must be in the gas phase if you want to use Kp. If you have some in the gas phase, some aqueous, then you can only use Kc. You can only go on concentration. You can't go on pressure. So in dealing with compounds in the gas phase, the equilibrium can either be determined based on the concentration or the partial pressure. And it's either or. You can't mix the two together. It has to all be concentration or all be pressure. Up to this point, we've only been doing Kc calculations based on the concentration of the various constituents. But the expression is going to be set up exactly the same way. So for an example, we have carbon monoxide and water in the gas phase. So we are going to include that. Goes to CO2 and H2. So my Kp, same thing, product over reactants. It's going to be the partial pressure of CO2 multiplied by the partial pressure of H2. And in the denominator, my reactants, partial pressure of CO and pressure of H2O. Everything has a 1 for an exponent, so all my coefficients all my exponents are 1. So that would be the same thing. If I had a coefficient of a 2 in here somewhere, that would become the exponent. So it's written exactly the same way. Instead of brackets that represent concentration, I now put a P in that represent partial pressure. Like you saw with the homework, there's a way to convert between Kp and Kc. So if you're dealing with a gas phase reaction, we can convert back and forth between Kp and Kc. And it's a relatively simple expression. Kp is simply Kc times RT raised to the delta F, where R is the gas constant, T is the temperature in Kelvin, delta N is the number of moles that are involved in the reaction. So moles of product minus moles of reactant. Again, gas species. It's only going to be the gaseous species. So for a quick example, PCl5 is going to decompose to form PCl3 and Cl2. I have a K for this, 3.26 times 10 to the minus 2 at 191 degrees Celsius. So I want to convert this Kc to Kp. My Kp is going to equal 3.26 times 10 to the minus 2 times R. My T is the 191 plus 273 equals 464 Kelvin. And my delta N is simply 2 moles of product. I added my coefficients, so 1 and 1 is 2, and 1 for the 1 reactant mole that I have. My delta N is 1. So in this case, it just gets raised to the first power, so I ignore that. And the math works out. Kp is simply 1.24. It depends. That has a unit of joules to it. This is because we're talking pressure. This has to be the atmosphere. So be very careful with which value of R you're using. If you're talking pressures, make sure that you're looking at the units that there's a pressure unit in there. It's usually going to be atmospheres. And if you're talking energy, like you were with the Arrhenius equation, it'll have a unit of joules in there. On the exam, the constants are usually given right in the question, so that shouldn't be an issue. They're also included on the equation sheet that's posted on Moodle. They're there as well, so you'll have that on your equation sheet, but they're generally right into the question, so that should not be an issue. But it's something to double check. Any other questions? Yep. Yes. All right. So we'll give you one to work on. Give me the second clicker today. It is. Yeah, there's no absolute value sense, so it is like whatever works out to be. last few answers in, please? All right, anybody else? Once, twice. Got the same numbers last time, so I think everyone's got it in. All right. So working through this one, and this is not too terrible. KP, KC, RT, delta N. Delta N in this case is 3 minus 5, or a negative 2. Right? And that's completely legitimate to get a negative value for your delta N. There's no problem there. My T is 900 degrees Celsius plus the 273, or 1173. So KP is 0.28 times the 0.08205 for my R value. My T is the 1173, all raised to the minus 2. Simplifies down. 96.24 raised to minus 2. And KP ends up being 3.0 times 10 to the minus 5. So D. And 90% of you got that. So that looks good. Any questions with converting between KP and KC? Alright. So that's going to be the end of the material that shows up on the first exam. So you can put a line in your notebook or however you want to do it. Anything else that we cover is going to not appear on the exam on Thursday. Alright. So that's the end of section 15.3. Yes.
What are the equations that you're going to give us?
They're posted on Moodle already. There's a Word document on here. All right. We're not done for the day, obviously. I already lost the day, so I'm already behind. So we got to keep moving. We got to keep moving here. All right. So section 15.4 is disturbing the equilibrium. We call this the Chatelier's principle. And by disturbing the equilibrium, what that is simply talking about is we've got a reaction that's reached equilibrium. We've added in our reactants. We'll let the reaction proceed until we reach that plateau where our concentration of our reactants and products is not changing anymore. Once we reach that point, now we do something to the environment of the reaction to shift it, to make it not at equilibrium anymore. And what will happen then all of a sudden it's not at equilibrium. So now the reaction is going to reshift. Now the concentrations are going to change as it goes back to reestablishing equilibrium. So the concentration of the reactants and products will change until we get back to equilibrium again. So we reach that plateau in concentration. And then it'll just stay at that new equilibrium. So we can disturb an equilibrium in one of two ways. We can change the temperature. Or we can change, let me spell right. We can change the concentration of either reactants or products. And by that, it's either we in some form or other, we either add some reactants or products to the reaction vessel, or we take them away. Either way, we'll obviously shift the concentrations, and that'll shift the equilibrium. If you're talking about only gases, you could also change the volume of the container. That would change the pressure, and that would also shift the equilibrium if you're dealing with gases. So for every action that you disturb the equilibrium, the system is going to readjust however it needs to reestablish that equilibrium. shifting to the right or shifting to the left, shifting towards generating more products or shifting to generating more reactants. So that's how it's going to go one way or the other. So you only have two options as far as which way a reaction is going to go. So again, we can add or remove reactants, we can change temperature, we can add a product. Really quickly, this will be posted. So in terms of adding or removing a reactant or product, in all these cases, my equilibrium constant does not change. But the equilibrium is going to shift direction. The K isn't going to change, but the Q is. Our reaction quotient, because that, remember, that's the number that we generate to indicate whether or not the reaction is going to change, and that's based on our concentration of reactants and products. So if we're adding and removing products, we're shifting off equilibrium, so we don't have a K value anymore, but we do have a Q value. So that's what we're going to see. You're going to change the Q value. So if I get in a situation where I'm adding products, that changes my Q. And now my Q is greater than K. And we know what that's going to do to the reaction. When Q is greater than K, which way does the reaction shift? How many people say to the left? Good. I won't even ask for the right. You guys all agree. Right. It's going to shift to the left. Right? So you can, just by looking at your Q and K values in that comparison, we had that short little table. We know which way it's going to go. Same thing if I add reactant. My Q is now less than K, and the reaction is going to shift to form more products. It's going to shift to the right. So of course, we can get into some calculations and a nice table with dealing with this. Okay? So by changing concentration, how is that going to affect the equilibrium? How does that change our equilibrium concentration? So a quick example. We have butane. It just all by itself is kind of going to rearrange and form a different compound called isobutane. This is what we call a rearrangement. It just shifts form. We're not adding or removing any constituents, any atoms to it. It's just going to rearrange to a different form. This has a K of 2.50. And the way this problem would be worded would be when equilibrium has been established, my concentration of butane is 0.20 moles per liter. And isobutane is 0.50 moles per liter. So the reaction, I put my starting material in, I let it come to equilibrium. These are the concentrations that I initially get. Now, once I've reached this point, I'm adding 2 moles per liter of isobutane is added to the system. So that's how I've disturbed it. I've added some product to the reaction. Calculate the concentration of both the reactant and product after it reestablishes equilibrium, this new equilibrium. Yes?
What's the number after the butane constant?
0.20.
No, I'm talking about before that. The one in between, like, is that 2.98 or?
This right here set up a reaction, we got it to equilibrium, we added some product to it, and it's going to reestablish equilibrium, and we need to find those new concentrations. So we've got an ice table again, just has a fourth line to it, fourth row. So we have our initial concentration. Now this is our initial equilibrium concentration. So that's going to be our 0.20 and our 0.50. Now the new line is our concentration just after addition. So this is what did we add in to disturb the equilibrium. So in the case of butane, we didn't add anything. So that doesn't change. And for isobutane, we added 2 moles per liter. We have a new concentration of 2.5 moles per liter. And just like we've seen it before, we have a change. We don't know what that value is, so we're going to use X for it. But which one's going to be positive, the butane or the isobutane? What's going to be the positive value? The butane is, because we added to the isobutane. There's too much isobutane now, so that's now going to be the reactant. So that's going to have the minus X. And this is going to have the plus X. So my new equilibrium expression are those. So you have to know which way the reaction is going to shift in order to know which one is essentially going to be the reactant. And in this case, to reestablish equilibrium, the isobutane is going to be the reactant. That's going to decrease in concentration. So the K for this is very straightforward. Is my 2.5 minus X over the 0.20 plus X. I keep it in this way even though the reaction is disturbed and going one way. I was given the expression here where I'm going butane to isobutane. That's the way the reaction was given to you. So that's how I write my K. My product, the way it's written, is isobutane, so it's going to be isobutane over butane. Yeah.
Can you go back to the previous slide?
I don't have time for that.
Sorry, you're adding the concentrations together, and I know that you can't just add one concentration together, just add one. Because it depends on how much of the concentration you actually have. I just think it's confusing that you're adding the concentration to get your final concentration for isobutane.
Well, no, I'm not adding to get the final concentration for isobutane. With the 0.5 and the 2, that's the new starting concentration. I was at equilibrium with a concentration of isobutane of 0.5, and at that point, that concentration is not going to change. As long as I leave the system alone, it doesn't change. But I don't leave it alone. I add in isobutane. Okay. So what that means is that's just like starting over again with a new concentration. The reaction is not at equilibrium now. So now that my new concentration at that point before anything happens is 2.5 moles per liter. Now the reaction is going to progress. I'm going to use up some of that isobutane and form more butane. Okay, so the reaction is going to progress. I'm going to use up. So now the concentrations are going to change. And that's why I have the X and minus X. And then we get to the new equilibrium at the bottom. Okay, that makes sense?
You might have misunderstood.
Come talk to me about it. Alright, so I have that, and I know my K was 2.5. So I just work through, I end up with 2.5 minus X is 2.5 times 0.20 plus X. 2 equals 3.5x. So I have an x value of 0.57. So my new butane concentration plus 0.57, 0.77 moles per liter, and isobutane minus the 0.57, 1.93 moles per liter. So the approach is exactly the same. The setup is exactly the same. There's just that one extra line to take into account how I've disturbed equilibrium. What I've done is